It won't be long now before you too can enjoy a view like this. Economy or business class? There will be a variety of choices of carrier and cabin. The view will be spectacular. This is the traditional way to orbit, a Russian Soyuz launched from Kazakhstan. NASA has to pay in the area of $70 million per seat return trip, and prices are about to go up. Only the Chinese have an alternative launch system. Very shortly, there will be 2 carriers taking tourists into space on suborbital flights. Blue Origin will probably launch first with their capsule and reusable launcher. Next will be Virgin Galactic and their suborbital space plane, launched from beneath a carrier aircraft and landing like one too, although to what altitude is still not known. Then you have America's return to space with its 2 commercial partners. Boeing have their CST Starliner, the first launch-capable capsule already off the assembly line. Looking every bit like an Apollo spacecraft, it will be able to ferry crew to and from the ISS. An unmanned test launch to the space station is imminent, and the crew has been picked to undertake the first few missions. Their standout competitors are SpaceX and their manned Dragon capsule, performing the same vital service. They're hedging their bets in the tourist sector as well, with their BFR concept naming their first paying customer.
Thank you, Hiro. Thank you, everyone. Wow. I am from Japan. My name is Yusaku Maezawa. You can call me MZ, please.
After the success of the Falcon Heavy maiden launch, SpaceX is ramping up design and construction of its even larger rocket ship to Mars. However, the 2 other commercial entities aren't resting on their launchers either. Jeff Bezos' Blue Origin has developed its BE-4 engine to power an orbital delivery system, and they have the US Air Force on board. Not to be left out of the market, Virgin has also developed a small payload orbital system, Virgin Orbit with its Launcher 1. Flown to 35,000 feet, slung beneath Cosmic Girl, a Virgin 747, the two-stage rocket can lift up to 500 kilograms into orbit and an inclination up to 120 degrees. Dream Chaser is still in the running with its pilotless shuttle, still under development for long-duration orbits. The late Microsoft founder Paul Allen's company Stratolaunch has unveiled the largest aircraft in the world, a scaled-up airborne launch platform with multiple payloads from the existing Pegasus rocket to a medium and heavy launch vehicle and a reusable spaceplane in the future. In the meantime, there is no shortage of conventional launch systems competing for their share of the market. From the USA, Europe, China, India, Japan, even Israel and New Zealand. The key to any launch system is, of course, the engine. The smaller, lighter and more powerful, the better. They pose many design problems. Fuel type, reignitable, chamber pressure limits, sea level or vacuum exhaust nozzle shape, but above all, reliability and cost. This is the Avio rocket factory in Colleferro, Italy. Here, engineers are developing the carbon fiber casing for the solid propellant rocket stages of ESA's new Vega-C launcher. To build them, 5,000 kilometers of carbon fiber impregnated with epoxy resin is wound around a pre-made metal mandrel. This produces the very lightweight but sturdy casings for the first, second and third stages of the Vega launcher. These casings are later fitted with an engine and loaded with solid propellant. One of these solid propulsion engines is the P120C. It was recently successfully tested in Kourou and is the largest and most powerful monolithic solid propulsion rocket ever built. With this new rocket, ESA hopes to respond to launcher market demands. The agency is also looking for value for money. This new engine is designed with the latest immersive technology and leading-edge materials and processes. Mass production will bring down the unit cost, but the design is for both Vega-C and the strap-on boosters for Ariane 6.
So certainly in the launcher sector, the competition is growing worldwide. But we believe that the European answer, the ESA answer with Vega-C and Ariane 6 is the right answer. In an aggressive manner, we are trying to make things more and more competitive. One of these examples is the joint solid rocket motor that we are developing across the two programs, the Vega-C and the Ariane 6, the P120C solid rocket motor that enables the possibility to harmonize resources and to have the same motor serving the Vega-C as a first stage as well as the Ariane 6 in both configuration as a strap-on boosters. So this is a very good answer to tackle the competitiveness aspect.
With Vega-C, the C stands for consolidation, ESA is further developing Vega. It will add increased performance to the flexibility of the current system without increasing the costs. Today, Vega can launch up to 1.5 tons on a 700-kilometer orbit. With Vega-C, it will go up to 2.3 tons. In order to increase performance, two new solid propulsion engines have been developed, the P120C and the Zefiro 40 for the second stage.
It is clear that whatever we develop has an exploitation objective. So we do not develop rockets just for the fun of it, but we develop rockets that need to be exploitable, therefore competitive in the worldwide market. And that's the way we are working hand in hand with industry to prepare them to walk on their legs in the future throughout the exploitation phase.
Further enhancements are made with Avom Plus, which is derived from the current Vega's Avom upper stage. Investing in new rocket motors also means investing in new launch facilities.
We have foreseen a lot of activities to modify the launch site from the Vega configuration to the Vega-C configuration. Vega-C is a heavy, larger and length launchers with respect to the Vega one. So for this reason we have to modify the hatches to the stages, increasing the diameters for what concerns the first stage.
Other changes include modified fluid services and installation of a more powerful crane needed to lift the heavier second stage of Vega-C. During these modifications, the site has to remain operational for the scheduled Vega launches. In the end, the launch site will be compatible with both launchers. With Vega-C, ESA is also working on related products such as the Space Rider, based on ESA's experimental re-entry vehicle IXV. It should allow for payloads to be sent into orbit and later return to Earth.
In addition to this, we have other products like a specific adapter for launching into orbit small spacecraft, so enabling the possibility of universities and research centers to access space at limited cost, so coping with the payloads which go from 1 kilogram up to 500 kilograms. We also have early elements of definition for a platform called Venus, which could allow payloads to transfer from orbit to orbit.
One unit which has been around for years and is still the Ferrari of rocket motors is the Space Shuttle main engine. Four of them will be mounted on the long-awaited Space Launch System. Reusing proven shuttle technology has saved time and money. The solid rocket boosters have been extended and tested. The Aerojet Rocketdyne RS-25 motors continue to roll off the assembly line. Fabrication of the immense components, cryogenic tanks, intertanks and fairings continues. The Orion capsule has flown once. The second flight-ready capsule is being prepared for the grand show. There is one more critical piece of kit required, perhaps one of the most important sections for keeping the astronauts alive: the service module. At Airbus in Europe, they have delivered the first flight-ready unit for the launch. The European component will house the electrical power, life support and propulsion unit for the Orion spacecraft, and like a giant pocket watch, every component is carefully and painstakingly assembled.
The European service module is part of an entire spacecraft built by an American company, Lockheed Martin, under the contract of NASA, and we are part of that. And of that spacecraft, NASA, Lockheed Martin is building. We are providing the European service module. We are providing the powerhouse of that entire spacecraft. That means we are providing the propulsion system, so the thrust to get into the dedicated orbit we would like to fly with the spacecraft. We are providing the air condition, I'm saying. That's the thermal control system of the entire spacecraft. We take care of the heat, which has been generated in the capsule, which has been generated out of several electronic components in the European service module as well. And we are making sure that that heat gets radiated into the outside of that spacecraft. On top of this, we are generating power. Our solar array wings are producing that power. We are conditioning that power and deliver that to the crew module and deliver that to the batteries which are located inside the crew module. And finally, we are also providing what the astronaut need to have to live in that spacecraft. That's mainly water in terms of the consumables, and that's oxygen and nitrogen to generate the atmosphere in the crew module itself. On the power side, we are proud that we have installed hardware which has already been flown several years ago on a shuttle. So the big engine we are flying here, the OMS-E, was a challenge for us to bring that into the vehicle. This is not new technology in that sense, but the integration itself, that was really for us a challenge that was new. We're preparing ourselves to be ready for the final integration with the rest of the vehicle, and then we are ready for a test campaign in the US, which is including several environmental tests, several functional tests. That lasts a couple of months, up to that point where the NASA team is handing over the spacecraft to GSDO, to the launch campaign, so that the vehicle can be put onto the launcher, and then we are ready for flight.
The first engine is the big engine, which is coming from the space shuttle. With this big engine, we performed the big transition maneuver to go to the moon or to go back to the Earth. So we can see here the auxiliary thruster, which are red. We have 8 of them coming from Aerojet. Here we have the OMS-E, so the main engine, but without the nozzle, which will be integrated in one of the latest integration steps. We can see here the propellant tanks. We have 4 of them, 2 for each propellant.
ATV, basically the automated transport vehicle here in Europe, played a significant role in terms of opening the door for that specific joint work on that spacecraft. It also played a role that we learned our lessons with a kind of that service module. Finally, the components we have flown on ATV, there are not so many which we carry on in the Orion European Service Module. We have a couple of them, mainly auxiliary thrusters, yes, on the RCS thrusters, and also a couple of tanks like our pressure tanks, but there are not just a few items which we carry on from ATV into the European Service Module design.
The difficulty here for the human spaceflight is the change of mindset. So to think that we are here in this space mission, we are flying human, and it's not like a rocket which is only flying with a satellite. Therefore, we are putting more effort on the safety aspect. We have a lot of redundancy. Each change we introduce, the smallest change we introduce in our system has to go through the safety boards, our safety boards, ESA safety board, and then the program safety board, to be sure that we can bring the crew back home safe.
With Orion and the service module certified, the sky won't be the limit. We will see ships refueling in orbit, a gateway station with a return to the Moon, then on to Mars and beyond. Opening space to industry and exploration, spaceflight will become the norm rather than the exception. Mining and manufacturing in orbit, power production, and habitats. One day, it might be as easy as driving to work in that red convertible of yours.